Hello. So today we're continuing to talk about our chest X-ray pneumonia detection implementation with attention mechanisms. To remind you, we chose this data set since pneumonia detection is highly subjective. Most doctors don't seem to agree on whether a patient should get diagnosed with it or not. It's also very highly dependent on X-rays, which means if an AI could accurately determine whether a person have pneumonia or not, it would speed up their diagnosis. So for our baseline model, we chose the DenseNet with attention layers of CBAM. This was due to its moderate parameter size with its very respectable accuracy. But we didn't just have the DenseNet. We also, in this upcoming milestone that we're going to talk about now, we implemented some changes. We added a function that could help us add fully connected layers, and we added a function that could also help us input convolutional layers. So in milestone one, we tried to implement the backbone with data augmentation to see and the weighted loss function to see whether or not it would still suffer due to our imbalanced data set, having a 3-to-1 ratio of pneumonia to normal. This worked kind of well. The data augmentation definitely helped, which made us think that to add a weighted loss function as well. So we added that, and after adding a weighted loss function, it was our best performing model. So now we're going to talk about milestone 2 achievements. So in milestone 2, we added an extra convolutional models to extra convolutional layers to our model. We also added a fully connected layers to our model, and we created multiple models to test which model would perform the best regarding our dataset.
Hello everyone. Moving on to the enhancements in milestone 2. So we introduced extra convolutional layers to better handle the grayscale nature of chest X-rays. And as you can see, we created a new class called DenseNet with extra conv end, which adds basically a sequence of conv value layers. For example, we have channels like 16, 32, 32, and 64 using 3x3 kernels, tried one and padded one. Then we follow that by a max pooling and a 1x1 convolution. So this kind of like pre-processes the input before feeding it into the DenseNet backbone, and basically it helps us extract more features from the medical images. And through the experiments we did, we had some variants like the 2conv max pool model showed that basically it improves feature representation. Moving on to the next slide. So our improvements in using progressive freezing. So here we modified the training function to support freezing the DenseNet backbone for initial epochs up to 6 in some runs. And we used set backbone requires grad, which this function basically set to false, which after it we unfreeze for fine tuning. So this mechanism basically stabilizes the learning on the pre-trained ImageNet weights, and it prevents the overfitting early on. It also helps the progressive attention training, and basically it helps the models converge faster and achieve better accuracy during longer training sessions. After that, we fine-tuned the hyperparameters and we extended the number of epochs we train on. So actually, we lowered the learning rates significantly considered to milestone 1, and we added weight decay for regularization, and we managed to basically increase the training epochs up to 25 epochs for train. Yeah, and then basically we use the same process for the different models that we tried training. So now we move on to the results that we had. In milestone 1, our accuracy was 81.09%, and it was somewhat good, like according very close to standard, but it wasn't good enough. So right now, the progress, we managed to test different models, and basically we managed to get, at first we had 83% accuracy, and that was using a variant of our model which had 4 convolutional layers, and we added a fully connected layer after that. And we also managed to get better performance with a different variant, which is 87% accuracy, which was just a basic model, but it was enhanced with balanced sampling using the weighted random sampler with a 0.5 ratio. And then we managed to get to 89% accuracy, which basically was using two additional convolutional layers before the DenseNet part. And we also added one extra fully connected radio layer at the end with a dropout of zero point 0.3. So these were the progressive improvements. And at the end, we managed to get the best performing model, which had an accuracy of 90.54%. And this was the weighted model. As you can see in the confusion matrix, basically had much fewer misclassifications, and also the heat maps, we did not include them here, but were also much better. For the next steps and the timeline, basically we have three more steps that we're looking at, and that is the first one is the multi-scale attention fusion, which we intend to implement by November 20th, which is basically modifying the CBAM architecture at multiple resolutions and using a feature pyramid for the fuse maps. After that, by November 27th, we intend to implement the unfreezing biphases of the CBAM modules, and then eventually, or like after that, if we have enough time and we see that it's going to help, we intend to add more features to the hybrid loss function with regularization, and that's hopefully to be completed by December 2nd. As to our contributions, so I myself, including Milestone 1 and Milestone 2, handled data visualization. I implemented the baseline model, the DenseNet 121 and the CBAM modules, as well as the visualization of the outputs. And in Milestone 2, I handled the hyperparameter tuning for the models that did not have the fully connected layers, as well as training them. For Adham, he focused on, during both milestones, on data augmentation. He also implemented the hybrid weighted loss. He also worked in this milestone on the fine-tuning the fully connected models as well as implementing the weighted sampling mechanism. And he also added the extra convolutional layers for the models that needed it. Thank you for your time. It was a pleasure presenting our work to you.